talk on a topic which is perhaps quite away from what you have been listening till now. This is mostly on the interfacing of theory with actual experiments. And the kind of experiments which I would talk about are from the domain of your most favorite domain. One of the reasons why you became a theoretical chemist is because you don't like organic chemistry. Yeah? And one of the reasons why someone became organic chemist is because they don't like physical chemistry. So this is how the boundaries and territorial integrities are maintained globally, if not in India. So there are this lack of communication between the two communities. One who is busy doing experiments. A lot of time is spent in running column chromatography. If you have friends in organic, most often you would see them in this posture, looking at drop-wise how the eluent comes into the conical flask, and they end up spending a lot of time. Another situation which you would have perhaps worried about their life in general and would have assumed that it is perhaps boring, that they run column chromatography often trying to separate compounds. And another scenario that you would have noticed, if you walk, you have the habit of walking in the department through the corridors, and if you have a nice olfactory reflex, that means your nostrils are in working condition, then you would have sensed overheating of oil bath. There is a characteristic order when you overheat oil bath. That means you have no idea how far, how long, how high you want to heat. You keep on heating. Because what is a common perception is that, oh, if reaction is not working. If reaction is not working, what will you do? Turn the knob, right? Whether the compound would disintegrate, whether it will eliminate a molecule of carbon monoxide, so you're willing to take all the pain, you would just increase the temperature. That's a standard approach, right? So when you increase the temperature, what do you think would be the physical basis? Assuming increased temperature led to success, you did get the product. So what would be the rough readout from this action of increasing temperature led to the product formation? What would be the readout? Yes, you are perhaps able to now cross the barrier with enhanced temperature. That is one submission that one can make. These are all qualitative. And I am known for my qualitative way of interpreting sometimes very complex reactions, chirality and stuff in organic reactions. So we would deal with a few organic reactions. When I say few, already you are scared. But I will help you. This is not that much scary. But before I go into any of this, so we have already uttered the word kinetics. And what is the closest species? If I create a concept map starting from the root node of kinetics, what are the other nodes it will branch out into? What are the other related words? Kinetics, fine. Kinetics can be connected to kinetics. This is one node. This can be connected to another node. What is it? Okay, thermodynamics. I will put it down here. Thermodynamics. Many energetic terms. What is the closest word associated with kinetics? Rate. Rate. Barrier. Activation barrier. Arrhenius equation. Pre-exponential factor. Collision frequency. Orientation. Heat. Temperature. Kinetic theory of gas. So you have to quickly respond to a number of concept map words after words. And when you respond, a bunch of ideas come together. Like the kinetics is associated with rate, and a clever intervention there, rate would also be associated with another very important node, that is catalysis. Yeah? What do a catalyst do typically? What do a catalyst do? Lowers the activation barrier, and what would the word catalysis in society would mean? Even political leaders use the word now. Synergy and catalysis. Speed up things. Speed up catalysis towards prosperity. Catalysis towards something, catalyze the growth of economy, etc., etc. So the speed is closely associated, rate is closely associated with another term called catalysis, where you will have bunch of catalysts which would help carry out reactions at reasonable time and reasonable conditions. A reaction which would have otherwise worked at 100 plus degrees Celsius, under catalyzed condition, it may work at room temperature. It is a huge gain. When you go from 100 degree, you have to spend a lot of energy to maintain 100 degree, to sustain the reaction which will continue to give product, but that 100 degree is not affordable in year-to-year basis if you are running a company which produces a product which will require 100 degrees Celsius temperature to be maintained for the reaction to make it happen practically. It's not a good thing. A huge energy cost associated with it. So therefore, when it comes to catalysis, if you can decrease the required temperature from 100 degrees to say 30 degrees, which is our room temperature, and in Chennai it is 37 perhaps. If you go to Delhi it is 46, and you can decide your own room temperature depending on where you want to carry out the reaction. You can tell your advisor if you work in Chennai that my reaction is not working, let me go to Delhi. And it wouldn't make any sense and any connection. Why do you want to go to Delhi? Here you have all the facility. No, room temperature, I want to do the reaction. So it is 46 there. So always there is a connection with available energy and this temperature and the speed at which the reaction would take place. And sometimes the speed is so fascinating aspect that if you use a catalyst, you do get the product before you graduate. I'm talking about 5 years of PhD. And if you are under a research group, which advisor puts a lot of pressure on students, I've been waiting for this results for so long, and sometimes the voice will modulate. All the intonations and cadence would be such that whether it is a very caring word of advice or expression of frustration, you don't know how long should I wait for the reaction to take place. And then you would respond, sir, but perhaps if you know the kinetics of this, we can do a clever intervention as to what temperature to select, what solvent polarity to choose, and perhaps a good catalyst which would make things happen. So it is very, very important that all these, of course, there is a lot of advertisement I can do for the whole domain of catalysis. Industry thrives, chemical industry thrives on catalysis. There's a lot of activities, and many of my former students were absorbed by pharma company. And they are doing DFT calculations, they are looking at reaction mechanism, they are looking at activation barriers for elementary steps in a multi-step reaction. Elementary step in a multi-step reaction would simply mean that you start from reactant, you have a transition state giving, say, intermediate 1. This is your classic SN1 reaction which forms a carbocation intermediate, and followed by maybe a taller barrier, shorter barrier, intermediate 2 before you actually go to product P. So this is a multi-step reaction. And when you mix the reagents, perhaps you have no idea whether or not there exists an intermediate, whether or not they are stable intermediate. I would use these words very carefully, stable intermediates, or whether or not there is a barrier which is surmountable at the temperature of your choice. Barrier which is surmountable at temperature of your choice. And when you carry out the reaction, the oil bath smell that you noticed is a reflection of, oh, I am busy doing the reaction, but I have no idea what's going on. Until you have the TLC plate. Any one of you have seen TLC plates? Small TLC plate where they would take a capillary tube, put that into the ongoing reaction vessel, take a sample, and then put a drop and look for whether product is formed or not. So if you see with respect to the baseline, one spot here, and this is your reactant, and you have a new spot which perhaps is characteristic of product formation, and then you are having a happy day. But oftentimes you see only one spot, which is that of the reactant, no reaction happening, increase the temperature, the moment you sight that second spot, you are happy. But you have no clarity on what is going on in the backdrop. How do molecules collide? Do they have enough activation barrier to overcome? and there are many entities which are involved. We generalize using this double dagger notation. These are transition states. These are transition states. These are first order saddle. These are first order saddles. First order saddles on potential energy surface. I'll quickly take a detour and describe what is this potential energy surface. I'm sure most of you know, you're from theoretical chemistry background. So you have a bunch of atoms, bonded, assume it's bonded, and any deviation from the equilibrium bond distances, bond angles, dihedrals, and any other non-covalent interactions which are present, the energy of the system would vary. Okay, so if you plot all of them, that is, let's say the Q is a generalized coordinate whose mapping with respect to the potential energy can be simply considered as a potential energy surface, which is incredibly complex. It's a hyperdimensional surface because there are so many degrees of freedom. Any small fluctuation will change the energy, so it is nearly impossible to do a complete mapping of potential energy surface. So as chemists, oftentimes we live with a reduced dimensional PES, reduced dimensional potential energy surface, where life looks much simpler. For example, if I consider a reactant going to product and assume I1 is the product in this discussion. So reactant going to product, and I can isolate this. I use the word very carefully. I can isolate this because it's my product. I can characterize them using standard spectroscopic methods, or I could take some signatures out from this intermediate and say that intermediate 1 is now formed. After, say, an induction period of few minutes to hours, you can isolate intermediate 1, and that did not happen in the very first minute. There is a slow build-up of intermediate 1 whose presence could be detected using spectroscopic method. So you're intervening to the solution or the reaction medium to be able to isolate or detect the intermediate 1. So you say that reaction is progressing. Reaction is progressing. So when you look at progress of reaction, let me bring a very simple example. So I have a nucleophile, let's say X minus, excess electrons in it, X minus, and I have a carbon attached to a living group, and I have 3 more substituents on this side. This is the tetrahedral carbon, nothing complicated there. Tetrahedral carbon, and I have an incoming nucleophile, because it has excess electrons in it, and it can push its electron into what is known as an antibonding orbital between carbon living group. That antibonding orbital, these concepts come from very basic qualitative molecular orbital theory. So you can essentially do a Schrodinger equation solution on your electrophilic partner. This is the electrophile, and you get stacks of MOs which are present in this molecule, and one of those frontier molecular orbitals, the one which has highest energy, or molecular orbitals which are found in the higher energy regime of the manifold of orbitals which are present. Because I say this is a usual misconception among students, that I have several bonds and I have lone pairs on this living group as well. So all of them are placed, all these electrons in the system are placed in several molecular orbitals. So I can tentatively call them molecular orbital 1, 2, 3, 4, 5, depending on total number of electrons which are there, and each of them is doubly occupied in all standard conditions or standard species, or the reactions of the kind which is described here. So each one is doubly occupied. But there is one orbital that determines the property of this molecule, and that orbital is the one which would matter. Whether this would act as a electrophilic partner, because we are talking about an encounter between a nucleophile and an electrophile, so there should be a willingness on the part of this species to be able to accept electron. That is why we call this kind of species as electrophile. So if this is electrophilic partner, it is acceptor of electron, it has to accept, always keep in mind that when you solve Schrodinger equation for this species, that is just the electrophilic partner, you don't have the nucleophile in the vicinity at all. I'm talking about the actual hands-on application of reaction modeling using DFT or wave function theories. In the static picture, I'm not bringing dynamics, the complexity, the layer of complexity due to dynamics of it. I'm not considering the collision. I would assume that this is linearly approaching with respect to the carbon leaving group. So this is an assumption, but I'm now solving Schrodinger equation for this electrophilic partner and only electrophilic partner, just because I want to understand more about this species which contains a living group on it. And I earlier said there will be a stacks of molecular orbital decorating this. So MO 1, 2, 3, etc. Most of them are doubly filled depending on what kind of, how many electrons are present in that given system. That is where it becomes transferable as well. Because when you learn a concept, when you learn qualitative MO theory on a system bearing carbon leaving group, and you would realize the value of frontier MOs, realize the value of frontier molecular orbitals. I want to emphasize that because a large part of chemistry is about reaction. Large part of chemistry is reaction. Just this earlier today, when I was having lunch with my friend and his son, I said that in chemistry there is so much academic politics. The statement makes sense? You agree or not? In chemistry departments in the country, there is so much of academic politics. And then this innocent son, like who is just out of college, asked me, why is it so? I gave a one-line response. Because chemists are reactive. I didn't say chemists are corrosive, but I just said chemists are reactive. Say they react to, molecules react to the environment, react to the incoming electrophile, incoming nucleophile. They always want to change from R to P. R to P. They don't stay there permanently forever. Given ideal conditions, they want to convert into product, and we are looking at the microscopic level what is happening. What is that collision that converts this into another compound which is product here or intermediate one here. That's what I'm trying to emphasize on. So when you solve the Schrodinger equation for this species, you got a bunch of molecular orbitals differing in energy, differing in its orientation, differing in its properties. And there comes one molecular orbital right higher at the top, which is unoccupied MO in the frontier region, unoccupied MO in the frontier region. I will take like, HOMO LUMO in that region I would generally call as frontier region. This is an ongoing debate. Many organic chemists debate with me, HOMO LUMO is only frontier, and for me, HOMO -1 is also frontier depending on what kind of species it is going to encounter. It is not like universal that HOMO would only matter to the property or reaction. That's not true. It could be HOMO -1. Depends on symmetry compatibility, depends on whether hard or soft species is the encountering entity to which it will react with. So we cannot universalize that it is always HOMO that determines the reactivity of a molecule. It could be somewhere in this region. So if you generalize, it is frontier orbitals, frontier molecular orbitals that would matter, that would impart reactivity to molecule, and chemistry is about reactions. That's sort of the storyline which I'm building up, that chemistry is about reaction, and when molecules collide, they transfer electron. There is a donor in general and there is an acceptor. So here electrophile is my accepting entity. Electrophile is the accepting entity. Something which is electron rich is the donor entity, and donor will always donate to acceptor. Donor will donate to acceptor. Unlike in society, rich rips off poor. Yeah? Rich takes more money from poor and poor becomes poorer and poorer. Isn't it? Agree or not? Agree, yeah. So in molecules, it's way more democratic. It is always electron rich to electron poor, from donor to acceptor, a donor orbital to accepting orbital, And now, when you look at accepting orbital, there is something interesting. This is empty orbital. And you know that an orbital cannot have more than 2 electrons. What is that principle which forbids? Maximum occupancy in an orbital is 2. So empty orbital can only accept electron, not the filled orbital. They will have repulsion. So empty orbital can accept, and donor would therefore, the equivalent of this should be that a donor should be characterized by a high-lying occupied MO. High-lying occupied MO would be the donor, and an acceptor is characterized by a low-lying accepting orbital. So this is almost about 20-30% of organic reactions which you can generalize. That is an empowering feel that you would have, that when you know this, donor to acceptor interaction can generally describe organic reactions, which is quite a knowledge, quite a useful idea which you can apply to very many different organic reactions. And that is precisely the point of divergence when you were learning. Why you stopped liking organic chemistry is because there are so many named reactions. So many of them, right? So many of them. Some of those names you hate to remember because you forgot. You will immediately forget it's volatile, as much volatile as organic solvents. So organic chemistry is so volatile, with aided and compounded by named reactions, it becomes even more volatile. But concept, what is underlying chemical reactivity often seen in organic reactions are, there is a donor, there is an acceptor. A donor is characterized by high-lying molecular orbital, and the closest connection I can make with this DFT workshop is that we are solving, let's say, Confram version of molecular orbital implementation. You're solving it on a molecule, you get the stacks of MOs, and nature and energy of MO would determine what kind of reaction it can exhibit. That's the take home till now. What kind of reactions it can exhibit. Whether or not this species can act as an electrophilic partner in its encounter with a nucleophile, it depends on whether it has a low-lying, willing to accept, symmetry allowed, unoccupied orbital, then it may be able to accept that pair of electrons. Now, assuming this is more than willing to accept the electron, then we can go to the next step. So, we identified donor acceptor as central to the discussion here till now. So, if I complete this, so a pair of electrons coming in from the donor, which is the nucleophilic partner, intercepting the electrophile, pushing its electron, and there is a bonded pair of electrons here. If you simply look at the Lewis type bonding, 2 electrons make a bond, and if I push both these electrons onto the leaving group, I break that bond, because I can simply look at the bond order. Bond order is, what is the bond order typical definition? How do you calculate bond order? If you were to use bonding and debonding, how do you calculate bond order? Half the number of electrons in bonding minus number of electrons in antibonding. That is how the bond order is defined. So in other words, if I populate antibonding orbital between same pair of atoms with equal number of electrons as in its corresponding bonding orbital, what would happen to the bond? I am putting 2 electrons into the antibonding orbital of carbon leaving group. 2 electrons into the carbon leaving group antibonding orbital. So if I put 2 electrons into antibonding orbital, what would happen to the carbon leaving group bond? Bond will break. Bond will break. So the bond order here will go to 0. So that means if I continue to populate this antibonding orbital, I would get X will now be bound to the central carbon, and leaving group will leave the system. Leaving group will leave the system. It has no bearing to get connected with the carbon because now the bond order is 0. This is very, very simple high school stuff, chemistry, but I'm introducing chemical reactivity and trying to connect with how computations can help. Actual computations can help in getting to know more about this entity, which is quite exotic. This is quite exotic species transition state. I have spent 30 years of my research career looking at chasing transition states. So chasing them down to such precision that is fun of my research, that we look at transition states for complex catalytic reactions. That's the fun. I will show some of these transition state, how complex it looks and how fun it is to deal with. So here is the reaction of interest for us, and here is the product side. So from the reactant valley, so this is my reactant valley. So when I describe in terms of the potential energy surface, chemical reactions can be perceived as, viewed as globally, if you were to view from the top, and if you are imaginative, chemical reactions are transit from one valley to the other. Transit from or traversal from one valley to the other. Here is the reactant valley. In reactant valley, carbon leaving group was bonded, and this was the electrophile. That is my reactant valley, that is X minus interacting with this entity was the reactant side of the story, and as the reaction progresses, the bond order goes to 0. When it reaches the transition state, the bond order becomes almost half on both sides. So this carbon leaving group bond order becomes half, carbon X new bond order will become half, and then you have reached the highest energy point, the zenith of this transfer from this valley to this valley. So valley 1 to valley 2 being the product, and then you are talking about a reaction mechanism. Reaction mechanism. That is how a reactant converts to product, or a bunch of reactants come together and give you a product via the intermediacy, via the overcoming of a transition state, which is shown in a simplified way, reactant via the transition state to the product, and now I have traversed from reactant value to the product value through a transition state. Is that clear? So I have talked about a reaction which is classically there in textbooks, substitution nucleophilic bimolecular. This is called SN2 reaction. Those who have forgotten, it is reintroduced right now without you realizing that, oh, you were talking about SN2 reaction. Yes, indeed, I was talking about SN2 reaction. So this is SN2 reaction. This is the product value. This is the reactant value. And now I will spend a few minutes on the transition state, which is somewhere mid-path, midway between R and P, provided the incoming X, outgoing X are identical. Incoming X and outgoing X, outgoing LG, if that is also X, then how do you distinguish there is a reaction? So I can do a radioisotopically labeled heavier X minus, and this is lighter X minus, lighter X, then I can study that. So if incoming is X, outgoing is also X, then I would have my transition state almost at the midpoint along the progress of reaction. And of course, there is more involved concept called reaction coordinate. It would take more time to discuss, so I will skip that part. A very beautiful concept, and I should also acknowledge that the idea of reaction coordinate for chemical reactions is way more complex. The true understanding of reaction coordinate can come only through phase space calculation, which is way more expensive, unimaginably expensive. It is not practical for the kind of systems that we deal with. So we are happy with this reduced form of representation, where we can locate transition state when you traverse from reactant value to the product value, and there are a few indicators, few parameters, few guidance that you can look at by looking at one of the terms that we have written here is thermodynamics, and the other term we have written here is kinetics. So let me draw something more here. So if I have a identical reaction, the transition state can be found. The graphics does not look good, but let us. So transition state can be found, somewhat like a midpoint between R and P. Midpoint between R and P. for identical displacements. So in the context of SN2, incoming and outgoing are same. So the bond order, etc., would be nearly as much as you are losing here, building here, it is being lost in the carbon leaving group part. So this is the typical scenario for TS found at the midpoint. It may be somewhat easy to locate such transition states. But if you have a scenario where your reactant is here, and the product is very much more thermodynamically stable, much more stable than the reactant. So then you have a transition state which will resemble the reactant, closer to the reactant, because your product is far away. When you look at what is the, see, this is the energy, this is the potential energy axis, and this I am tentatively calling it as progress of reaction. So in this sense, the potential energy of the product is very different from reactant. That means the nuclear configuration is very different with respect to the reactant nuclear configuration, the position of the nuclei in 3D space. So here you would be able to find a transition state. If it exists, it's not guaranteed that there is always a transition state. So you can find the transition state in closer difference with respect to the reactant. A small change would be able to take you closer to the transition state for this sort of energetic difference between reactant and product. So what I am trying to say is that awareness of thermodynamics of reaction, that is energy difference between product minus reactant, that will help you. Where do you search for transition state? What should be the initial guess for X to C distance and C to LG distance? The incoming and outgoing group, what would be the geometric positioning of incoming and outgoing group? That is one aspect which would be central to successful locating of transition state. However, transition states go way beyond that, because if you look at this, what is happening to this umbrella, which was pointing towards me from this side, and when it goes to product, it has flipped over to the other side. So that means something midpoint at the transition state, you have these three groups coming into a near planar arrangement with respect to the leaving group and X. So there are further things happening beyond the critical distances between X and C, C and LG. There are dihedral changes happening. So the central carbon has to go from a umbrella to a planar and then flip over. So one would have to take into account, that is where the chemical intuition becomes very, very important in locating transition states, and which can frustrate you. Transition state identification on PES can be really a frustrating, daunting task, but when you get one, you get more. But to track down the first one in a given family of reactions can be a pain, but it will come with experience, come with chemical intuition. And I said that there is accepting orbital, donor orbital. So accepting orbital, in this case, the sigma star accepting orbital will, if you were to plot it, you will get an accepting orbital which will look like this. This is the sigma star orbital between carbon and leaving group. This is the direction in which it is oriented. I said the frontier MOs would determine reactivity, the property, whether or not this species is compatible with the X minus which is coming in, and what direction X minus should approach the electrophile. Again, this directionality is mandated by the orientation of the accepting orbit, orientation of the sigma star, which is along this LG bond direction. That is one of the reasons why X minus come from the rear side. This is a usual textbook thing from early high school. You're all taught in SN2 reaction, the nucleophile has to come from the rear side. Nucleophile has to come from the rear side. And if you ask a question, why should it come from rear side? You would respond by saying, it cannot come from the front side. When I was in 7th standard, I was asked the question, what is an insulator and what is a conductor? Okay, from electricity transfer perspective, in that module, what is a conductor and what is an insulator? So I said that something which is not a conductor is an insulator. So if I ask you a question, why the incoming nucleophile should approach the electrophile from the rear side, that is exactly opposite to the direction of the leaving group, you would say that it cannot come from the front side. That is not the response. It doesn't capture MO perspective, MO picture. It doesn't capture what is accepting orbital. It doesn't capture anything about frontier molecular orbitals, which is at the center of what we are discussing. So this is the accepting orbital. Hence, the best donation can happen in this particular cone. If you imagine a cone, in this cone, the best interaction between the donor and acceptor orbital can take place. And this also helps you think a little bit back in the days when you ever did a salt analysis, detection of chloride, bromide, iodide. Anyone remember salt analysis? How do you detect if I give you a dilute solution of a sodium chloride, dilute solution, silver nitrate, you will add silver nitrate. If I give you sodium bromide, you will add silver nitrate again in another test tube. What will be the difference in observation? Color would be one difference. How about iodide? How about time that it takes? Sodium chloride will give immediate precipitate, white, puffy, immediate precipitate. The bromide solution, these are all things post facto. You know it. You remember that observation. You have an intuition that bromide will form slower, pale yellow precipitate. And what about iodide? Silver iodide? That will also be formed. But how about time that it will take? It will take longer time, slightly longer time to form. It won't form as fast as the silver chloride, which is immediate. But in all cases, within few minutes, you get silver iodide, silver halide guaranteed within few minutes. But that is not the case with organic reactions. That is not the case with SN2 reaction. That is not the case with aldol, Manic, Claisen, Diel-Salder. That's not the case. You wait, wait and wait. You heat and wait, heat and wait. It keeps going. Is there a clue lying here on the board? Is there a clue? Why would the silver halide formation, two spherical entities colliding and forming a lattice, forming a precipitate, two spherical entities, think of direction of collision, two spherical entities, Ag plus, Cl minus, any direction of collision, almost guaranteed formation of silver chloride, silver halide. But is that the case here? I talked about this cone. If the incoming nucleophile with its pair of electrons with the donor orbital is not approaching this entity from any other direction except this cone, it is not seeing that accepting orbital. And now think of it, actual sense, chemical reaction, and assuming this is done in solution phase, you have a container, you have electrophile and nucleophile, you mix them in a solvent, and you are stirring it using magnetic stirrer, and each molecule has its own kinetic energy. When it is translating in the vessel of reaction, we can simplify if you are more concerned about solvation effect and all. Let's simplify a gas phase reaction. Okay? So these electrophile and nucleophile are moving at so much speed at room temperature. So much speed, it's a hell lot of kinetic energy at room temperature. They're moving at so much speed, and each of them have their own degrees of freedom, vibrational, rotational. So can you imagine all of them put together, how fascinating the molecular reactions are going to be? So they are moving around and they are rotating, tumbling around, and within it each bond is vibrating 3n-6 vibrational degrees. It is exercising that vibrational degree of freedom. When you put together all, you would begin to wonder, why would a reaction even take place? Because they are moving so fast, so much. Yeah, there is an energy guarantee. Product is stabler than the reactant, so there is a driving force. If you get the product, it stabilizes the system and so on. But collisionally speaking, if you don't get this alignment, this orientation, that is why out of millions of collision, only one would be able to build what is known as a pre-reacting complex. That is something which I want to introduce. So I started with R, but there is something called pre-reacting complex, a very important but underappreciated concept among organic chemists. A pre-reacting complex is an interesting entity where X minus and this electrophile, like if I may attempt to animate, somewhat gross, this is my X minus and this is my electrophile with its leaving group and tumbling around, moving around. They hit in different directions, nothing happened. So at some point, a feeble donation started happening. X minus started seeing that accepting orbital. So you see, if like I'm trying to animate, like not just that I am getting animated, but I am animating the whole process. So X minus moving around, no collision, effective, like anywhere, and now you will see some sort of concerted movement. Yeah? Concerted movement, because the weak donation started happening, so they move together, fall apart, no reaction. Again, move together, effective donation, zip, LG goes. And that is what is happening here. That is the TS. And that is what we call, in a diminished form, we call reaction coordinate. Reaction coordinate for us, reaction coordinate represents this sort of collective vibration. Okay, I will dare to say this in front of theoretical spectroscopists and so on. So this is a collective mode where you lose one vibrational degree of freedom and reappears in the form of translational degree of freedom. So here I have these two species. That is why I am introducing the idea of pre-reacting complex. Instead of directly saying X will react with this and give you product, X would have to come together, form something called a pre-reacting complex, which is not any measure of stability you can attribute to pre-reacting complex. They just move together. They just stay together. And it is not infinitely long. They have very short lifespan, but they just stay together. They just move together. And in that collective species, you have one more atom, one more entity coming together. So your 3n minus 6 vibrational degree of freedom, one of them would get stiffened, and that is what appears as reaction coordinate that will help you go from the reactant value to the product value. That is one of those aspects that makes a transition state have what is known as a transition state, which is a first order saddle point, is characterized by, Suraj, are there any practical examples on transition state coming up in the workshop? No, there is no visualization of transition state. They will not locate a transition state. Okay, so I will show some examples in the animation. So the characterization of a transition state requires that you spot this reaction coordinate which appears in the form of imaginary frequency. Imaginary frequency, which would require a vibrational frequency calculation on the transition state. And here I also want to emphasize the beauty of computational chemistry. The beauty is that you can calculate energy for any exotic atomic combination. Any exotic, whether molecules exist on the face of the earth or molecules exist in interstellar space or far away in stars. So any configuration, you can evaluate energy. You can check whether or not they satisfy the criteria of zero residual forces on each atom. If so, we can call them a minimum energy structure. That's the beauty of computational chemistry. That you can calculate any nuclear configuration, look at whether or not they are minima or a transition state, or what would be their energy with respect to some reference point. This is the advantage. So that very same advantage, I am capitalizing, I am exploiting that advantage that transition states are such an exotic species. A typical lifetime of a transition state is 10 to the power minus 12 to minus 14 seconds. People have spent their entire career chasing transition states experimentally, such as Ahmad Zewail in Stanford. They tried to locate, they tried to detect, forget about isolation, they tried to detect transition state using extremely sophisticated spectroscopic method, high power laser and so on, and there have been some success stories. But number of characterization of transition state, when I say characterization of transition state, on a potential energy surface, you are actually talking about a transition state whose structure, that is geometry, structure is known, structure is identified, whose energy, by solving, let's say, our famous h of psi equal to d psi on a transition state, you know the energy, you know the geometry, and you can therefore locate transition states on potential energy surface. This is hugely empowering, that you're being able to locate a transition state. The advantage is that when you have the energy of a transition state, and it's rather straightforward to get the energy of a minimum energy structure, such as a reactant, and then you are all set to calculate the barrier for this step, barrier for this reaction. So if you can calculate barrier, you are in for kinetics. You are in for commenting rate of reaction. You are in for getting into the whole domain of catalysis. That's where transition state becomes so crucial that it's non-trivial to locate transition state. I can tell you 10 times harder with respect to a standard minimization of a ground state species. Ground state species, it is like, of course, ground state species can get confounded by number of conformers. There can be, real pain in the neck. If it is fluxional molecules, there can be numerous conformers. But one thing about transition state is that once you master the art of locating transition state, which calls in for knowledge of orbital interaction, geometry, alignment, and what is actually that chemical reaction. So that is a requirement to be able to successfully locate the transition state. Once you have the transition state, you're all in for commenting on the kinetics, commenting on the speed of reaction, commenting on whether or not you can design a new catalyst altogether for transition, if you have knowledge of transition state. Now, are there questions? Is it making sense? You expected a lot of equations which I'm not showing. There's no computer on. So I'm like disappointing you guys? No? Serious no or strong no or weak no? Okay, so are there any questions? Yes.
Certain reactions we call it kinetically controlled, thermodynamically controlled. So how do we distinguish them? Is it just based on the barrier height and relative positions?
Yes, that would be the simplest way to look at it. It's a very important question. Industry puts in a lot of money to understand whether a given reaction is likely more kinetically controlled or thermodynamically controlled. So thermodynamic control directly refers to the stability of the product which is in equilibrium. Okay? Kinetic control refers to speed at which a given disappearance of reactant is taking place or appearance of one of the products happening. So it is about speed, the other one is about stability, and if the barrier is low, that would be the product which you would cite it first. But that does not guarantee that in longer duration, prolonging the reaction, you would ever see that product after a long while. And why is it industrially important? There are some very interesting actual examples which have happened in industry. Imagine an alkyne triple bond, Ar triple bond Ar, and on alumina surface, Al2O3, and you are subjecting this alkyne to hydrogenation. You are adding H2 across the triple bond. And this is the actual real story. So in industry, and this was an important hydrogenation reaction, and they want to stop at double bond. They don't want to hydrogenate completely to alkane, but they want to stop at alkene, the intermediate between alkyne and alkane. So they want to stop at the double bond level. That means only one H2 should be added across the triple bond. So interestingly, in this particular alumina supported hydrogenation of alkyne example, in about first 30 minutes, you will only get cis-alkene. So this would be the product that you would get, AR double bond cis-alkene. So the hydrogen is added on the same side. This is the outcome in first 30 minutes. Wait for 90 minutes, you will have this as the only product. Trans. Trans is more stable. In this case, trans is more stable. So, give that prolonged duration, the system stabilizes into thermodynamically most stable product. Because now the reactant and product is in equilibrium, and equilibrium will be dominated by most stable product, and this is the one at 90 minutes and more, this would be the exclusive product, but at 30 minutes, this would be the major product. Now, imagine you are doing it in tons and tons of kilogram annually, and your product that will fetch you revenue is only this. The other way around. The product that will fetch you revenue is only this. So this is not interesting. This is not going to bring any glory to company, any commercial advantage to the company. You are only interested in the cis-alkene. Here comes the value of kinetics. Here comes the knowledge of transition state. Here comes the importance of knowing the kinetics of reaction at industrial level, supported hydrogenation system. And if you were to set up the reaction, go for tea and come back in 1 hour, company will run into loss. Whereas you had the awareness of kinetics, the early induction happens, this would be the product, and if you knew that this formation of this has a lower barrier, if you knew that, you would make more profit because you will stop the reaction, quench the reaction round about 30 minutes, and you don't want to make this at all. So look at the interplay. So answering your question, this is the thermodynamic product, this is the kinetic product. So if you are quenching the reaction, stopping the reaction around 30 minutes, you are using the kinetically controlled product formation. You let the reaction go on forever. You are exploiting thermodynamic factor of the reaction, leading to the most stable product. Many, many examples are there which are industrially important. So therefore, knowledge of transition state, and I've said at the beginning that it takes extremely sophisticated experiments to detect transition state. But in computation, it is much, much cheaper option to locate transition state because you get many things for free. Once you locate transition state, you know their structure, you know the energy, you know the orbital interaction, you know many, many other aspects which you can further use for your design of new catalysts and so on, which is precisely what we do in my group. So this is a fascinating species. Are there, you had a question? Yeah.
So I was just, so you introduced the frontier orbital concept and then the potential energy surface, right? So how do they map? So the orbital energies are a metric for the energy differences?
Orbital energy, see, these are species which has n number of molecular orbitals in it. And so is all these species. What I am saying is that the trigger for separated reactants to form a pre-reacting complex involves interaction between frontier orbitals or between the donor and acceptor. So it begins to move together and fall apart, move together, fall apart. So this is the earliest donation. Inception of this donation would ensure there is an affinity between X minus and this species, this old molecule. If not for that affinity, you cannot expect a transition state to be ever reached because this is rigidly geometrically controlled. If you don't have this approach, then you don't have the pre-reacting complex and hence you may not be able to reach the transition state. That's the point being made. The frontier orbital wise, the highest occupied orbital of this species, lowest unoccupied orbital of this species would matter. So these orbitals are the one which enables the formation of pre-reacting complex.
Is it more related to the Arrhenius factor, the pre-exponential factor?
Yeah, so this gets captured into pre-exponential factor because there is a huge cross-section aspect and the collision. This collision only is effective and any other collision from any other direction would be like they would fall apart. They're not going to lead to the pre-reacting complex. So I would submit that for successful identification of transition state requires access to or awareness or knowledge about pre-reacting complexes, because that will set the stage. And if I go back to another textbook example, and many of these reactions won Nobel Prize. Many of these reactions. The Woodward-Hoffmann rule comes from orbital interaction, orbital symmetry driven reaction. So if you have a diene and a dienophile, okay, and the textbook would write diene, dienophile like this, no reaction will happen. No cyclohexene will form if you were to go with the textbook model. So this is how most textbooks will write. This plus this giving this cycloalkene as the product, right? So this is all on the plane of the board. And they don't lead to any product if they were to collide on the plane of the board. They have to collide with their planes parallel to each other, so that they can see the donor and acceptor orbital, they can trigger the HOMO-LUMO interaction. And that is why the directionality of collision, which in turn would impact how fast your product would begin to form. There is a huge directionality because of the donor-acceptor orbitals which are involved. I just shown one example, a beautiful interplay of orbital interactions in all these Nobel Prize winning reactions such as Diels-Alder reaction. They're hugely governed by donor-acceptor orbital interaction. They have to come align in a manner such that the pre-reacting complex is like this. This is my diene, and the pi orbitals will be here, and dienophile pi orbitals will be here. So diene, dienophile approaching like this or colliding like this among several other collision will only lead to product. Only this will form the PRC, and this will enable reaching transition state, otherwise it will fall apart. And hence it takes time. Hence it takes time to get to that PRC. And once you are in PRC, chance of reaching a transition state is higher. And if you're not on a PRC geometrically, you would never reach the transition state. That's the point. Any other questions? Yes.
You told about locating the transition state. What about the barrierless transition?
Barrierless transition. Yeah, people have studied that. There are some interesting examples where transition state is more stabilized through various interactions than the ground state and the product. So there are barrierless reactions, yes.
How it's locating?
It's just that the energy is lower than the reactant and product. Locating, if you are very skillful, you may be able to locate. Any other questions? Yes. Yeah, so you have to ideally you have to walk down from the transition state. So you do an intrinsic reaction coordinate to...
Although you are telling it is complex, actually it is not a complex, it is a transition state.
No, no. I am talking about, I did not elaborate. So this is the true first order saddle, and I am talking about a reactant here. So I will place the reactant. So this is the PRC, and I will place the reactant here now, so that this part is clear.
That means you are getting some kind of additional, say, zero Nemack place.
There is a dip, it is required.
Dip means anyway zero Nemack.
Yeah, so it would...
Getting it additionally.
Yes, you have to be able to locate. You don't actually go all the way to reactant in most cases.
I am telling if you do the, let's say, proper ES calculation. So will it exhibit that particular location with no imaginary frequency?
For intermolecular reaction, it is a must. It has to. But intramolecular, you don't have that, the orientational issues.
So in that case, I can call it an intermediate.
Yeah, it is an intermediate. We call it like pre-reacting complex may be a misnomer, but see, intermediate by definition should be amenable to detection. This is never going to be amenable to detection. That is why it's a complex. Like the initial years transition state used to be a transition complex.
No, but it is minimum from all sides.
Yeah, it is minimum from, that is why it is a saddle. It's a minimum from all other side. See, remember, whether you optimize a molecular geometry as a ground state or a transition state, you are effectively optimizing the entire molecule. Okay, so when you are optimizing, anyone talked about molecular optimization, geometry optimization? How many of you are familiar with geometry optimization using any quantum mechanical?
No, but it's slightly more complicated. You are actually very expert in this field. It is not a single molecule. So if you talk about the say geometry optimization of a single molecule, that's a much more easier situation. But here you are bringing in two such stuff. If you are getting the potential energy surface for a chemical reaction. Okay, that's different from just only molecule. I am getting the equilibrium structure of the molecule. So you have more than one or at least two reactants. So at every possible orientations, relative orientations of those two reactants, they should get reflected in this particular potential. So it's a potentiality surface associated with the chemical reaction. Not a
Yes,
single
yeah, it is. So I'm referring to energy minimization of a given geometry, be it a ground state, be it a reactant only geometry, or that of a transition state. Both are subjected to energy minimization. That means the ideal optimal nuclear positions and lowest energy. So Q versus E mapping, and you have to subject this into geometry minimization. The TS will be minimized as a first order saddle, and ground state will be minimized as a stationary point with zero imaginary frequency. So they are true minimum, but transition state is minimum in all directions except along the reaction coordinate. That is why it is called a first order saddle. And there are other levels of complexity that one would encounter, particularly when you deal with photochemically excited reactions. There are numerous complications like presence of conical intersection, so I'm not touching upon any of that. But when you actually practice locating transition state,
actually here you are talking about only ground state surface.
only ground state.
So there photochemical means you have to bring in another excited state.
Yes. Minimum S1 or T1 and so on. So that makes it way more harder problem. So here I am talking about dark reactions, not dark in any other sense, but just no light. These are all good reactions. So you have the transition state, and in the transition state you would locate the reaction coordinate, and when you visualize, let me show one animation. That is why I was not using the other computer.
But you are showing animation yourself.
Yeah, I know. See, so one of my former students.
I wanted to see your transition state avatar. So how does it look like a satellite?
So that will severely strain my degrees of freedom. So one of my former students, who is now a faculty at Princeton, so she was visiting and she asked me a question, "Sir, do you still dance in the class?" Yeah, so when I teach conformational analysis, I do all kinds of, the tricks to demonstrate that we have very, very large degrees of freedom just for arm. Robotic arms cannot match human palm. It has so many degrees of freedom. So I can tell you this, I can tell you this, I can tell you all kinds of things, right? So much degrees of freedom, and the robotic arm cannot match this, okay? They have very limited degrees of freedom. So if you...
I think the organic chemistry teachers will learn dancing also. To some extent.
It is by choice, right? So oftentimes the fear of judgment is what prevents you from dancing, right? As far as I am concerned, I have very, very less fear of judgment, because my conviction tells me how good I am doing things, such as this class or any other class I teach. I can read out from your eyes. Yeah, that is why I hate online classes. I hate online classes to the extent there is no online content from my side, okay? So you don't see any course of mine online. So when I taught...
By the way, I think the audience must know he is the national teacher. He got the award from the...
Thank you, but I liked Surat's introduction. R.B. Sunoj from IIT Bombay. That's it. That's all. That's all matters to me. Okay, so these days, they're all smart, but they would.
I should also tell he is known as the night professor.
Uh,
This is something which I like very much.
mind the spelling also. Huh? Not the knighthood, not the knighthood. So this is NIGHT. I just visit student hostel in the dining area a day before the exam. The day before the exam, I visit student hostel because that if I reach out to them, hundreds of students will come and ask last minute doubts because that is when they study. Yeah. Yeah, because they will bring all the, what is that? PYQ. Huh? What is PYQ? Yeah. So when any student asks me, sir, can you share PYQ? I will tell that I will share CYQ. That is current year's question paper. And I did, but with masking. And masking makes it so enthusiastic. What is that hidden? The question may be like, in the molecular mechanics framework, the terms such as this, although do not contain dash, dash, dash. So I will induce them into, there is a question on molecular mechanics force field. Okay, there is one. And then I will allow cheat sheet. They can bring one A4 size and font size predefined. I give a sample. So they can bring handwritten any material up to one A4 size paper. And this is fun. And at the end of exam, I take a survey at the exit. It's an exit poll. So I will stand there. One question. Was the cheat sheet useful? No, sir. So there are many techniques. Like I wish I could talk about teaching. I'm very fond of teaching. I don't teach much, but very fond of. Okay, so here is one transition state. Can you see why do I call this as a transition state? There is an imaginary frequency, and of course this will be very intimidating. If I can show here is a reaction. And this is by Benjamin List, who gone on to get Nobel Prize. And see, one more statement, all of you are researchers and you will have independent career and so on. So one thing I want to emphasize is that right problem at the right time, right problem selection at the right time is very, very crucial in your career. I am moved from topics to topics. I did not stay stuck with one topic. My tools are same, but I don't study same reaction forever. I don't stick in organocatalysis. I started my career looking at mechanism and solvent effects in organocatalysis, and 15 years later, organocatalysis got Nobel Prize. And at the beginning, when I was starting my career, I was only enthusiastic about organocatalysis, very fascinating class of reaction. No one looked at the mechanism, no one is aware of role of protic solvents in these transition states and so on. That was my motivation. But identifying right problem, it turned out to be the right problem because later it became a Nobel Prize winning reaction, right? So there are many, and at this point, I'm hugely into artificial intelligence, deep learning models for chemical reaction outcome prediction, very much deeply into it. I'm going crazy. It is so addictive that even in aircraft, I will be reading something or other related to this new domain. It's not very new. So the take home is that be on the outlook, watch out for contemporary interests, what are the hot topics, what are the problems, whether or not your tools may be applicable there. That's what I'm saying. I'm not suggesting that you quit your work and do something else. See, you're acquiring skills on some domain, and those skills are so useful for some emerging family of areas, emerging areas. So useful, but you have to make that connect. So I'm trained as a computational chemist looking at organic reactions, properties of organic molecules, but independent career, I really wanted to get into transition states, catalysis, so I did that and persisted for 23 years, and it had given me enough pleasure that I'm happy about. So I'm saying again what I said earlier, that for me as a teacher, it's the readout. It's looking into your eyes and how your eyes communicate without you realizing. That's my best pleasure. So if the class is going good, you don't have to tell me class went well, and oftentimes, students come and tell me your class was very good, and my response will be, thank you. And the moment I forget, I don't keep it not more than 3 seconds, anyone tells, anyone compliments. Although natural human tendency is to feel good about it, enjoy, be in that moment, yes, I do feel good, but I don't carry it beyond 3 seconds. Why? Why I don't carry beyond 3 seconds is because you will be pained by criticisms. Yeah? We will all be pained by criticism. I was kicked left and right in my early career. Left and right, I cannot elaborate in a public forum. So I had gone through my own pain. So those were so painful that people who talk nice in front of you would kick from behind. So this is the standard classic Indian academic politics. And I'm brutally open. You can talk to me outside the class. You can learn many things about academic politics, but then unfortunately that is the case. People who talk nicely in front of you, the moment you are gone, they talk bad about you. So I'm just prepared for that. Whosoever says whatever, I don't care. I don't care. I know what I do. I know how happy I am. I know how I do my things. And I don't need certifications. Sorry. Yeah. If you have a compliment, yeah, I will take it. If you have criticism, tell me directly. You're a computational chemist, you're a software guy. I'm ready for a debate. Let's be fair. I'm ready for a debate, but don't talk at my back. Come directly in front of me and talk to me. And without that software, I can bet you're not going to spot transition state of this kind. Without that software, don't blame the software. Seriously, don't blame the software. And these softwares are not made by trivial people. These are led by activities of John Popple, who had a vision. John Popple, Krishnan Raghavachari, numerous people whom I know in person. They are not fools because their name reflects in a software. This country had criticized software too long, too harsh for no gain. No gain. So I'm ready for a debate. Yes. So coming back to this, our business, how much time I have? Done? Huh? 15 more. Okay. So here is a reaction. Very simple reaction. Don't look at this complexity. This sulfur receives one oxygen from this H2O2. And every one of you knows what is hydrogen peroxide, the simple reagent, and water is a side product for this. So this is an environmentally good reaction. And now why would one be interested in this kind of compounds? This is precisely the family of compound one would take in the form of omeprazole, pantoprazole, all those prazoles. Why do you take omeprazole, pantoprazole? For what? What condition? Hyperacidity. That is what the early career would reward you with. Hyperacidity. Yeah? Early career and PhD will reward you with hyperacidic situation. You will have belching because some harsh comments you heard behind you. You will have hyperacidity. To suppress hyperacidity, you use chiral sulfoxides. That is why this reaction is important. Chiral sulfoxide. So then now, what is my toolkit? What is my expertise? Transition state. Look at kinetics. Study catalysis. So we studied catalysis. Someone who studied catalysis got a job also. I will tell you who studied that catalysis. This very hard problem to tackle. This is transition state located by now Dr. Garima Jindal, faculty in organic chemistry, IISc Bangalore. The first ever hire of a woman faculty in organic chemistry is history of 100 years. First woman faculty proudly is my student who located this transition state. Cool, cool. And I can bet, if not for Gaussian, which has been thoroughly criticized, if not for Gaussian, I bet no one would locate this transition state. And who did algorithm implementation in Gaussian is Bernie Schlegel, one of the best scholars I have come across, who is an expert in quantum, who is an expert in potential energy surfaces, who is also the person who implemented transition state search algorithm using what is known as a Bernie optimization algorithm, and hence this transition state, hence that catalysis. Therefore, let us not be hypocritic. Let us be very clear. If you are dealing with practically relevant transition states relevant to important catalysis problem, Bernie optimization algorithm would help you locate the saddle. This is one example. And what is that imaginary frequency that I'm talking about for this side of the audience? So here is this H2O2, hydrogen peroxide, which will split and transfer the oxygen to thioanisole. The SME receives that receives that oxygen. That is the reaction coordinate. H2O2 splits and OS bond forms. H2O2 splits and OS bond forms. For this side of the audience, H2O2 splits and it is transferred to O of this sulfur. This is the substrate. And that is a reaction coordinate. That is how a transition state is characterized, that it is indeed the transfer of that simple innocuous oxygen to sulfur, giving you value-added product such as sulfoxides, and this is done in chiral condition, therefore you get chiral product. And of course, we would go ahead and characterize those transition state, look at many interactions and so on. So this is just to show that you can look at transition states of complex systems. And this was done many years ago, and Garima went on to do a postdoctoral work with Area Warshall, who is another Nobel Prize winner for QMMM kind of contribution. And then we continued with transition state business for more complex reactions where you have multiple catalysts in one pod condition. Because it's such an excitement. You cannot look at such complex systems. First of all, the mechanism itself is complex, then looking at transition state, and we have been continuing this journey of looking at chemical catalysis from our skill set, our toolkit. Our toolkit is what? To locate transition state, comment on the energetics, look at the barrier, look at thermodynamic feasibility, look at the structure, look at reactions in a holistic manner. This is what we do. Now, if you have located so many transition states, and somebody would say that, oh, it's good for you, you publish some papers. Okay, fine, yeah. That's what most academics do. Look at something and publish some paper, right? So we also do that. We look at something and publish some paper. And then the other side is that, oh, these are all known experimentally. Yeah, that reaction was published by Benjamin List, who is a Nobel Prize winner. Asymmetric sulfoxidation was a known reaction. We looked at transition state. We commented on the origins of selectivity, why this form of enantiomer is formed and so on. Fine. Can we do it in the other way? Meaning that, can you predict reaction outcome and then subject them to experimental validation? Predict first, followed by validation. And I would have to tell you a story that I inherit my research philosophy, research outlook and inspiration from the giant known as Paul von Rogge Schleyer. Paul Schleyer. Professor Chattaraj knows him very well. Paul Schleyer is my academic grandfather. My PhD advisor spent about 6 years as a postdoc. My PhD... I had beautiful 3 hours with Paul Schleyer describing my science when I was a visiting prof in University of Georgia. I got only 3 hours in my life. And there was supposed to be one more meeting with him, which never happened. So, such a great person.
I was there one summer, actually 4 months.
The Paul Schleyer was nominated for Nobel Prize for 3 times for 3 different discoveries. He was an experimentalist, turned to be a computational chemist, and Paul Schleyer is a person, like you guys would appreciate him by some other metric. His H index used to be 140. Yeah, and total number of publications by when he died was 1,500 something. That's the kind of person I'm talking about. So Paul Schleyer used to believe that if your computations are good, it should ideally be able to provide directions for new experiments. That is his philosophy. And when he talked about this, people laughed at, because computations were so trivial those days, like 80s, 90s, you don't have enough compute power to compute what you actually want to compute. So then came the DFT, like the previous lectures talked about the developments of DFT and Jacob's ladder and so on. So DFT with incorporation of non-covalent interaction, incorporation of dispersion correction had set in a new revolution of a different kind. new revolution of a different kind, that it empowered you to be able to predict outcome of catalyzed reactions. That is next domain that we got into. Maybe I will talk about that tomorrow as an example, because oftentimes theory computation is considered as an enabler for experimental research, and a factor that can, a knowledge that can help them accelerate their discovery pipeline, but it could happen in the opposite direction as well. So you can predict ahead of experiments, and I will show one or two select examples from my group that how could you predict ahead of experiments. And if anyone is thinking that can you really predict a whole new class of reaction, we are not there yet. But with AI implementation, in next few years, perhaps that is possible, that is already happening, that you can discover new reactivity which has not been discovered through human endeavors yet. So things are happening in that direction. So I said earlier, pick right problem at the right time, and this may be applicable when you do your career planning. And there is a lot of prospects identifying what are those emerging areas, and that comes only through literature familiarity. More you read, you become better at forecasting, better at seeing long horizon, predicting what is the new directions science is likely to take. With your own skill set, you can branch out. Thinking outside the box and trying to plan your future, etc., by knowing what is happening in your domain, and while retaining your tools and skills, you can branch out and address some very, very important problems or topics. This is a gathering of youngsters. Ensure that you pick right problem at the right time, and you can always ask me this question, how do you know it's the right problem? In hindsight, maybe, yes, it appeared like a right problem that you picked, but how do you know it's the right problem? Look for the trends. Look for the wind direction. You hold your sail when you are in high seas in the direction of the wind, so that you can sail faster, sail better, and reach a shore of success, reach a shore of satisfaction. But if you don't hold your sail, you don't sense the wind direction, you are in the mid-ocean. That's the figurative way of saying this. So be familiar with literature, and I have all separate some 6 hours, and some of you would have taken that course called Communication Skills and Research Methods. I teach 6 to 8 hours just on how to read primary literature. 6 to 8 hours. Just how to read a published paper in your domain. How to cope up with the vast ocean of literature. Every second there is a new paper in chemistry. Every second. No exaggeration. More than 1,500 journals in chemistry. How in the world you are going to cope up? So what are the techniques to cope up? How to read, different forms of reading, etc. Sorry, I'm deviating from the concept of this workshop. But back to this reaction. So you can use power of computations to locate transition state, study kinetics of reaction, engage in designing new catalyst, interpret existing catalyst by using the language of structure, geometry, energy, and you can look at the feasibility of reactions using the energies of reactant and product. You can comment on the thermodynamic feasibility, whether or not a reaction is likely kinetically controlled, thermodynamically controlled. So your interventions are largely on the PES, potential energy surface of reaction. That is the kind of application of DFT which I wish to convey to you, that DFT can be extended to chemical reactions. You can look at intermediates, transition state, energies, and so on. And molecular property is another domain which I do not wish to touch upon. Professor Chatraj, Professor Saurabh, they all have done lot of work in conceptual DFT, looking at hardness, softness, Fouquet indices, global reactivity descriptors. So tons of work out there. And they would act as a guiding principle, what is likely the site of reaction. So here I assumed that, this is the site of reaction. But in a very large, complicated molecule, you may not know what are the sites of potential reaction given a reaction condition. So there could be numerous sites leading to byproducts, side product, disintegration, not the actual product that you thought would happen. So all those works are important. just by looking at ground state attributes of molecules. Again, it involves computation. Because remember, when you solve Schrodinger equation, you know everything about the system. Depending on the quality of wave function that you can generate, you know everything about the system. Not just that you know everything about the system today, everything about that system tomorrow and n number of years to come. So I will leave you with a statement from, I think it is from Eliot. It reads like this: time present and time past. Time present and time past are both perhaps present in time future, and time future is contained in time past. Blew your mind? Anyone wants to repeat? Make an attempt? Give it a try? At least like first 3 lines. Time present and time past are both perhaps present in time future, and time future is contained in time past. I repeat, time present and time past are both perhaps present in time future, and time future is contained in time past. What I am describing is wave function. You think about it overnight, and tomorrow, first lecture is mine. I will ask you what is your interpretation, why a wave function can be described poetically like this. Time present and time past are both perhaps present in time future, and time future is contained in time past. That is wave function. Back in 20s, when hydrogen atom was solved, you got a wave function. Those days, higher order polarizability or higher order terms or many atomic properties were unknown, not discovered, no experiments done. Same wave function is useful when they got discovered. Yeah? So now you connect with the statement. Time present and time past are both perhaps present in time future, and time future is contained in time past. Once you solve it, once you solve h of psi equal to psi, you have access to wave function. You can use it for very many different purposes. So you can use it for evaluating conceptual DFT molecular descriptors. You can evaluate for looking at their energy, geometry, whatnot. So it's very, very empowering. It's not like buy one, get one free. Buy one and get infinite number of items for free. That's the power of computational chemistry, that you solve Schrodinger equation once. You get so many properties getting printed. You have charges, you have it. You have dipole moment, you have it. You have geometry, you have it. You have molecular orbitals, you have it. And if you were to measure each of them, you require extremely sophisticated instrument. Just to study vibrational spectroscopy, you can put millions of dollars into that. Just to look at UV visible transition, same equipment will not help. You have to go to another lab, take that measurement. And if you are looking at nuclear magnetic resonance, you have to go downstairs into some basement, minus nth level of any building, so such that it can sink forever, eternally. The dead weight has to be withstood by Earth. So NMR measurements are done in such spaces. So you require another sophistication. So computations can give all of them at once and for free, except the computing cost that you would have to spend. Thank you.